Hey, what's up, guys? Okay, so in this video, I want to talk about one application of the Cauchy developer, which I feel like interesting. So share with you guys. This is called Erdos Ginzburg Ziv theorem. Okay, so given the theorem says that given a1 up to a2n minus 1, so you take any 2n minus 1 number belongs to some abelian group G. So G is abelian group with order n, and there are n of them. So you can always find n of them, right? So any 2n minus 1, you can find n of them, which sum to 0. Okay, in G. Okay, so basically you take any 2n minus 1, and mysterious, there are always n of them, which sum to 0. Okay. Then, okay, so let me just write down the right. So one maybe hard to understand. So one non-trivial corollary is that you take G to be nz, so z divided by nz. Then this gives you the following, right? This gives you any 2n minus 1 integer always exists n of them, which sum is divisible by n, or basically the multiple of n. Okay, and the simple example, right? The trivial example will be n equals to 2, right? If n is 2, then basically it says that every 3 number has 2 of them which sum to even. Okay, so so let me just write down. So every 3 integers, there exists the 2 of them. Sum is even. Okay, this is trivial, right? Because any 3 of them, there will be 2 of them has the same parity. So if you sum the same parity guy, must be even. And a little bit, you need to think a little bit when n equals to 3. This tells you that every 5 number have 5 integers. There exists the 3 of them, which sum is multiple of 3. Okay, and the proof basically, so you can see that if you take to 0, then you cannot take the third 0, right? Otherwise, that 0, 0, 0 will be summed to 0. So you must take 1, right? And maybe you take 1, but now you cannot take the third one, right? So last one must be 2, but then 0, 1, and 2 must give you 3. Okay, so if you only take the mod 3, then you can easily see this fact. But keep going is hard, right? Let's say every 4 of them, so every 7 integer, there are 4 of them which size multiple of 4, which is a little bit non-trivial, right? Okay, so actually it works for any abelian group, and the proof is not so trivial. Okay. So in order to do this, we need to use the Cauchy developer and the subset idea. Okay, so let me just give the proof after, but let's consider the simple proof. Let's consider G to be order prime. Okay. So give you the G, this proof that G must be Z mod PZ by the classification of finite group. And so let's say P is prime. Okay, the proof, let me just prove, right? So let me just recall the Cauchy developer, right? So if you haven't seen the proof of previous video, that you can check it. So Cauchy developer tell you that if you take any subset AB belongs to Z mod PZ, then the some subsets of this and have at least P, and basically size cannot be very small, must be at least greater or equal to A plus B minus 1. If you using this from like doing this for multiple set, then you will get the following. You will get that if I have a1 from n number and n set, if I sum of them, this sum set at least greater or equal to the minimum of P, and you sum over the number and the minus n minus 1. Okay. So right, you just keep apply this Cauchy developer. So now we can prove the results, right? So prove this EGZ theorem when G is order prime. So idea is that you take a1 up to a2p minus 1. You take all these like number, right? some element. Now you consider A1 as a set which is A1 AP plus 1, and the A2 which is a set A2 AP plus 2. Keep going until AP minus 1, which is AP minus 1, and A2P minus 1. And the final singleton set is AP, which is A2P minus 1. Oh, sorry, it's AP. Okay, and easy to see that it's just some partition. And so you first sort them, right? You first sort it then such that A1 less or equal to A2, up less or equal to A3, up to less or equal to A2P minus 2P-1. Okay, so now let's see. So if all the AR, if AI has size 2, size 2 means that these two are different, right? If they are all different for all I, then if you apply the Cauchy-Davenport, this means that the sum set A1 from 1 to P, at least the size, which is minimum of P, and the sum of them, right? So some of them are basically, you get summation AI from 1 to P minus P minus 1. Okay, now let's see this. So you sum over the set, right? But there are 2. So total is 2P minus 1 minus P minus 1, which is P. Okay, so this means that the minimum P and P is P. Okay, so this tell you that the sum of all this set as a set, right, must be the whole group. Right, so obviously that the 0 will be inside the whole group. Okay. And so if all these AR are different, let's say, so if all this A1 has 2 elements, A2 has 2 elements, 2 different elements, then it must be true. Okay. So we prove the simple case. We prove one case, right? But if, let's say, if sum of AK has only 1 element, that means that AK is the same as AP plus K. Then this proves that AK equals to AK plus 1 up to AP plus K. Right? So you will have P number. You will have like P number, which is the same. Right, so definitely, if you take all this, it must sum to 0. It must sum to 0. Okay. So we prove the results, right? Because if all these AR are distinct with basically size 2, then you apply Cauchy-Davenport. If one of them has size 1, that means that one of them are the same. Since they are the same, so you sum P of them must give you 0. Okay, so this proof is very interesting. So now let's consider the general proof. Okay, so let's prove the general case. Right, so you can like basically induction. We can make induction on group size G. Okay, so when G is 1, it's trivial, right? Basically. Okay. So since G is abelian, right? So I can take subgroup. I can take subgroup H inside G, such that G quotient H. This is an index, right? As the size of the G quotient G is prime. Okay, some prime number P. And let me just H equals to small h, just for the convenience. Okay, so the idea is very interesting. So now let's go to the proof. Okay, so now I have A1, A2 up to A2n minus 1 inside the G, right? So basically, I want to do induction, right? So I will say that this theorem holds for H, size H, and I want to say that the G quotient H is P, some prime. Okay, so if A1 up to A2n minus 1 is good, belongs to some group G, then I can view all this by quotient, by add H and become quotient group, right? So I can view all this sequence inside become A1 plus H, A2 plus H, up to A2n minus 1 plus H, where it belongs to G quotient H, right? Now, this is a long sequence, right? So I can apply the Cauchy-Davenport, right? Because now this guy is prime P, right? So I can apply Cauchy-Davenport claim that there are some of them. There are P of them sum to 0, right? So I can arrange the previous P number. I can rearrange the previous P number such that they sum to H, right? Because H is an identity inside the quotient group, right? So there will be let's say, let me just rearrange. Right, so if I rearrange it, I can say that, oh, there are A1 plus H, A2 plus H, up to AP minus 1, sorry, A2P minus 1 plus, sorry, there are P of them, so some H, right? AP plus H. All this sum to H, right? Now I can apply this again. I can say that so the remaining still very long sequence, right? So I can say that there are A2 P plus 1 plus H and AP plus 2 plus H up to A 2P plus H. Right. So all this also sum to H. And then now the sequence is still very long, right? I can keep applying. Okay. Until that until I get the following. I can get A like maybe here, right? So let me just do this. So I can keep applying the Cauchy Davenport for using the previous result, which is prime P. And until that I get something, right? Until that I get the let's see. So I can get, let's say, so I can get like let's say, so I want to get 2n minus 1 number, right? So I can 2n minus 3 P yeah, plus 1 plus H and A 2n minus 3 P plus 2 plus H up to A of 2n minus 3 P to minus 1 P plus H. Okay, you can check this is true, right? So basically you can fill all of this. Let's see. Sorry, 2n minus 3. There this is 2n minus 2. Okay, and you can so how many elements I use, right? I use P. So total I have used 2n minus 3 P. Sorry. So I have let's see. So yeah, so from this I have used. So this is I use A1 up to AP, right? And AP plus 1 up to A2P. So I have used 2n minus 2 P elements, right? Let's see. Oh, sorry, it's 2H. So I'm stupid, right? Because n is this P times H, right? So I'm stupid. So I use 2H minus 2P. And this is, so the total sequence, right, has 2pH minus 1. And I have used 2pH minus 2p, right? So there are remaining 2pH minus 1 minus 2pH minus 2. 2p. So I have remaining 2p minus 1, right? So final remaining 2p minus 1, I can apply the final Cauchy Davenport again. Right, so there will be some rest of them, some of them, which is A of, let me just relabel it to be 2H minus 2 minus 1P plus H, and up to like A of 2H plus H, 2HP plus H. Sorry, this is minus 2, this is minus 1. So 2H minus 1 times P plus H, and then 2H minus 2P plus H. Okay, so now let me just write down. So amazingly, what I get is the following, right? I get the P of them sum to H, P of them sum to H, P of them sum to H, right? So if I go back to the original sequence, this means that all this number sum becomes an element in H, right? So it means that this guy belongs to B1. And then this guy, so this guy is called B2. This guy is called B2P minus 2. This guy is called B2P minus 1. Okay. So, and all the BI belongs to H. Okay, all the BI belongs to H. Okay, so what I get is following. I get the B1, B2, up to 2PB minus B2B minus 1, such that bi, all of bi belongs to H. Okay, now I can apply the Cauchy-Dev report again. Oh, sorry, 2H minus 1. Sorry, I'm stupid. So this is 2H minus 1, right? Sorry, 2H minus 2. So I got B1, B2 up to B2H minus 2 and B2 2H minus 1, right? Because I can just separate this into different subset. Okay, so I got B1, B2 up to B2H minus 1, which all the BI belongs to H. Now this we can apply. So we can apply the induction on H, right? So my induction on H. So there is this the H of them, right? There is this H of them sum to 0. Okay, and this proves the results. Because if there are H of them sum 0, that means that you can find H of them, H of B. By the H of B comes from the subset, which is H of B. There are H of B, right? And each B is the P of sum of P term in A, in terms of A, right? So basically this says that there is a NH sum NH of them where sum is 0 in the original group G. Okay, so yeah, the proof is a little bit non-tricky. So non-trivial. So you prove. So this is the proof of this Erdos Ginzburg Ziv theorem. And see you guys next videos.